So now we're still in chapter 14, but now we're looking at a new functional group called amines. All right, amines are going to have this nitrogen here. You are not going to write the common names for amines. You will have to draw amines. You will have to describe their solubility, dissociation, and neutralization of amines. However, you're not going to draw them from their names. I might give you a molecular formula, and you might have to draw the different isomers that have an amine with that molecular formula. So amines are derivatives of ammonia, which is NH3, in which one or more of the hydrogen atoms are replaced with alkyl or aromatic groups. So you can see here in these structures, we have a nitrogen, and there are 3 alkyl groups. Here we have a nitrogen with 2 hydrogens and 1 aromatic group. Here we have a nitrogen with 1 hydrogen and 2 alkyl groups. Again, so for an amine, you're looking at a nitrogen, okay, that is going to have these single bonds. It will have this lone pair and be bonded to either hydrogens or alkyl or aromatic groups. Amines are classified as primary, secondary, or tertiary. We saw this designation when we looked at alcohols. However, when we looked at alcohols, we looked at that C-alpha, that alpha carbon that had the OH group. And we looked to see how many carbons were attached to C-alpha. Here we're going to look at the nitrogen itself. A primary amine has 1 carbon group bonded to the nitrogen atom. A secondary amine has 2 carbon groups bonded to the nitrogen atom. And a tertiary amine has 3 carbon groups bonded to the nitrogen atom. So again, for alcohols, you look at C-alpha, which is the carbon that has the OH group, and you determine how many carbons are attached. For amines, we're going to look at the nitrogen itself to determine how many carbon groups are attached. So here are some examples of amines. Ammonia, we have primary amine where you have 1 carbon group, a secondary amine where we have 2 carbon groups, and a tertiary amine where you have 3 carbon groups. Realize that the carbon groups do not have to be the same as they are here in this slide. So again, don't worry about naming amines. Let's classify these as primary, secondary, or tertiary. So for A, look at the nitrogen. It has 1 carbon group. This is a primary amine. For B, look at the nitrogen. It has 3 carbon groups, so this is a tertiary amine, 1, 2, and 3. So that you can see here, again, you do not have to write the common name. So no nomenclature for chapter 14. Again, we are not going to go through nomenclature. An aromatic amine is where you have this NH2 group attached to a benzene ring, or you have a nitrogen attached to a benzene ring with alkyl groups. From the solubility perspective, primary and secondary amines with fewer than 6 carbons are soluble in water. Thus, they can form hydrogen bonds with water molecules. Remember, you can form hydrogen bonds when you have an OH and an NH. Tertiary amines can form hydrogen bonds only with water molecules. That is because a tertiary amine has 3 alkyl groups and then this lone pair. So tertiary amines can accept a hydrogen bond. Primary amines can form more hydrogen bonds than secondary amines because they have that extra hydrogen. Tertiary amines have no hydrogen on the nitrogen and can only form hydrogen bonds with water from the nitrogen atom. That lone pair can accept a hydrogen bond from the hydrogen of water. Like alcohols, the smaller the amine, including the tertiary ones, the more soluble you are in water. As you increase the number of carbons in the chain, the effect of hydrogen bonding is diminished and solubility will decrease. So let's look at these structures. Which of the following compounds are soluble in water? You should see A is soluble, B is soluble, and C should be insoluble. Ammonia, as well as primary and secondary amines, act as a Bronsted-Lowry base. The lone pair on the nitrogen accepts the hydrogen. So remember, a Lowry base, a Bronsted base, is a hydrogen acceptor. When it accepts the hydrogen, it produces the ammonium ion and hydroxide. So here we have ammonia and water. It's going to accept a hydrogen. So here's my base, my Bronsted base, my Bronsted acid. This is my conjugate acid, and this is my conjugate base. Here you can see methylamine reacting with water to form the methylammonium ion and the hydroxide ion. Amines typically have a very strong odor. You can recognize that odor as almost a fishy smell. You can neutralize the smell of an amine by using an acid. So often you can see lemons squeezed on salmon to neutralize the fishy odor, and the product is going to be an amine salt. So here are some examples of neutralizing amines. So you have your amine, you add an acid, and you're able to form an amine salt, where you have a positive ammonium ion and you have a negative anion. Often, when an amine needs to be used as a drug, it is converted to its ammonium salt before being used as the drug. The ammonium salts are solids at room temperature. They no longer smell, and they're soluble in water and body fluids because they are in this ionic form. So here you can see some examples of ammonium salts used as the active ingredients in different medications. Ephedrine is used as a bronchodilator in the decongestant Sudafed. You can see it's ephedrine HCl. You have an amine salt. Diphenylhydramine found in Benadryl is used for the relief of itching and pain from skin irritants and rashes. Again, you can see that it is an amine salt. You have an ammonium ion and a negative anion. The narcotic cocaine is extracted from coca leaves using an acidic HCl solution. It is smuggled and used illegally in the form of cocaine hydrochloride as its ammonium salt. When you treat cocaine with sodium hydroxide, you form the free base, also known as crack. When a person smokes crack or powder via free base cocaine, the drug reaches the brain more rapidly and in higher peak doses than when it is snorted in powder form. The user feels an intense rush followed by a crash that can produce strong craving for more of the drug. That is why crack is more addictive than cocaine hydrochloride. Alkaloids are physiologically active compounds produced by plants. They contain nitrogen. They're used in anesthetics and antidepressants and as stimulants, and many are habit-forming. Here we have the structure of nicotine. You can see nicotine contains an amine. Many alkaloids have amines. Nicotine is a stimulant that increases the level of adrenaline in the blood. It also increases heart rate and blood pressure. Nicotine is addictive because it activates pleasure centers in the brain. Caffeine is also an example of an alkaloid. It is found in coffee beans, tea, chocolate, and soft drinks. It is also a stimulant of the central nervous system. It increases alertness but may cause insomnia. If we look at the structure of caffeine, we can also see that we have an amine. I'm just going to circle that group there because that is the only amine that is present. We are going to go through another type of functional group called an amide that is found in proteins. Amides have a carbonyl and a nitrogen. So you can see here that this is an amide and this is an amide, right? The only amine present, I'm just going to change colors real quick, is this one here that is circled in red. Morphine and codeine are also alkaloids. They are obtained from the oriental poppy plant. They are used as painkillers. So I'm going to highlight for you the amines here. There's an amine and there is an amine. Let's look at the other functional groups that are present. You can see here in blue, I have a phenol. And then here I'm going to do in green, I have an ether in morphine. And then I have an OH group. And I also have an alkene. All right, let's look at codeine. In codeine, I'm going to highlight the ether in green. There's another ether here. We have an OH group, and we have an alkene, right? And then last, we also have an aromatic, right? So this is the type of structures you're going to have to identify, the types of functional groups. I'm going to give you a complicated structure, and you have to identify the key functional groups that we've discussed. Right, so you're not going to have to draw the condensed structural formula or line angle formula for an amine when you're given the name. I could give you a molecular formula, and then you have to draw the different isomers, as I did in a previous video for the carboxylic acids. We are going to look at amides. As I said to you before, amides are found in proteins. An amide is when you have a nitrogen bonded to a carbonyl group. You're not going to have to write the IUPAC names, no IUPAC names and common names. You will have to draw structures based upon molecular formulas, and we will also look at the products for formation and hydrolysis. So amides are derivatives of carboxylic acids. Right, so if we look at our carboxylic acid structure, you have a carbonyl and an OH. In an amide, you are going to replace that OH group with an NH2 group or a nitrogen. It doesn't have to be an NH2. Amides are produced by reacting a carboxylic acid with ammonia or a primary or secondary amine and heat. Right, so here's your carboxylic acid. Here's ammonia. We have heat, and you are going to make this amide bond. Let's look at the second example. Again, same carboxylic acid group. We're going to react with a primary amine, and we're going to get an amide. Okay, so here the nitrogen has one hydrogen and a methyl group. Here the nitrogen has two hydrogens. What's key is that you have this carbonyl nitrogen. That's what defines the amide. All right, so let's predict the product of the following amidation reaction. There's your carboxylic acid. You have your primary amine. The product will have that benzene ring, your carbonyl carbon, your nitrogen, a hydrogen, and the CH3 group, plus water. So you're losing the OH and a hydrogen from the amine. Okay, you don't have to name amides, don't worry about that. You're not going to have to write the common names or IUPAC names for amides. You just have to work on recognizing that amide functional group. Urea is the end product of protein metabolism or nitrogen metabolism in the body. It is removed from the blood by the kidneys, and it's excreted in the urine. You can see here, urea is an amide. If the kidneys malfunction, urea is not removed, and it builds up to toxic levels, creating a condition called uremia. So as we looked at before at alkaloids, and we saw the amine group, many barbiturates are cyclic amides or barbiturate acid. Barbiturates act as sedatives in small doses or sleep inducers in large doses, and they are habit forming. So if we look here, right, you have a cyclic amide. Here's another, again, it doesn't matter which carbonyl I choose, okay? And let's look at the pentobarbital. You have an amide, you have an amide. So this is an example of cyclic amides. We looked at aspirin, which we found was an ester of salicylic acid. Aspirin substitutes contain phenacetin or acetaminophen. They also act to reduce fever and pain, but have little anti-inflammatory effect. All right, so if you look here at phenacetin, you have an amide functional group. If you look at acetaminophen, which is also used to reduce fever, you have an amide group. Okay? But again, little anti-inflammatory effect. So if you have a headache, right, acetaminophen is good for a headache, or fever. But if you have inflammation due to overuse of a muscle, you're not going to take Tylenol because it has little anti-inflammatory effect. So amides will undergo acid hydrolysis and basic hydrolysis. When they undergo acid hydrolysis, the products are a carboxylic acid and an ammonium salt. When they undergo basic hydrolysis, they produce the salt of the carboxylic acid and an amine or ammonia. Okay, so again, acid hydrolysis, we're forming a carboxylic acid, and you get the ammonium salt or the amine salt. If you have a base doing the hydrolysis, you're going to get the carboxylate salt and an amine. All right, so here we have to draw the condensed structural formula for the products when we have N-methylpentamide with NaOH. I'll give you the structure for the amide. So here's the structure of N-methylpentamide. You're doing basic hydrolysis. When we do basic hydrolysis, the products are going to be a carboxylate salt, and we are going to get an amine. So here the carboxylate salt will be sodium pentoate, and you'll get the amine. The way I want you to think about this here is that the OH is negatively charged, so that when you're hydrolyzing an amide with a base, you get a negative oxygen, right? Negative oxygen, negative oxygen. If we have the same amide, and we're going to hydrolyze with H+ and heat, okay, we are going to get the ammonium salt, or the amine salt, I should say, in this case, plus the carboxylic acid. So here I want you to think about this. This is H+. So we are going to make a carboxylic acid, and the positive charge will be on the amine. All right, so that sums up the carboxylic acid, ester, amine, and amide chapter. Remember, you need to learn how to identify these functional groups. As far as our reactions go, you learned how to take a carboxylic acid and an alcohol to form an ester. You learned how to hydrolyze an ester into its carboxylate salt and alcohol, and you also learned how to take an ester back to the carboxylic acid and the alcohol. So remember, this was done with an H+ in heat, and this is done when you break an ester into its carboxylate salt with the NaOH. Again, you're getting a negative charge on the oxygen, and you have a negative OH group. Okay. We also learned about carboxylic acids and their physical properties, how they can act as weak acids. We looked at esters and how they are volatile compounds. Amines have a nitrogen atom. That nitrogen atom is bonded to an alkyl or an aromatic group. We looked at their solubility. We looked at how they act as weak bases and how they react with acids to form amine salts. From the amide perspective, we learned about the amide functional group with a nitrogen and a carbonyl. We hydrolyzed amides with acid to form carboxylic acids and ammonium salts. Or you can hydrolyze an amide with the base to form carboxylate salts and amines. And again, remember at the base, negative oxygen, negative carboxylate salt. So that sums up chapter 14.